In this video, I will introduce basic circuit analysis to analyze a simple resistor-based DC circuit. This is part 1 of 2. In this part, we will determine what the theoretical currents and voltages should be through and across 3 resistors in a series and parallel network. In part 2, we will assemble the circuit and we will see how the measured voltages and currents compare to our analytical solution. To begin, let's first look at how we could analyze this circuit. It is neither truly serial nor parallel. In fact, we have this 100 ohm resistor in series with a parallel combination of a 470 ohm resistor and a 330 ohm resistor. Our power supply here will be a 5 volt DC source. So to begin with, let's simplify our circuit a little bit. We can combine the 470 ohm resistor and the 330 ohm resistor into an equivalent resistance. So let's go ahead and redraw our circuit with REQ drawn in place of these two, REQ being the equivalent resistance of those two parallel resistors. So we can go ahead and draw our power supply. It will remain the same. We will still have a 5 volt power supply. We'll go ahead and leave our 100 ohm resistor as is. And then over here, we will just draw one equivalent resistor now in series with the 100 ohm resistor that was already there. And if you remember, the equivalent resistance for 2 parallel resistors can be found by 1 over the sum of the reciprocals of each of the individual resistances. So 1 over 470 ohms plus 1 over 330 ohms. And if you do out the math on that, that works out to be approximately 194 ohms. So if you wanted to find one single resistor that could replace these 2 resistors in parallel, you could use a 194 ohm resistor. Now in the real world, 194 is not a standard value for resistors, so what you might use is a 200 ohm resistor. But for purposes of our complete analytical solution, we're going to leave the 194 ohms in our calculations. So now we have a series circuit, and we have REQ replacing these 2 parallel resistors. Now we can go about finding the current through this series loop just by using Ohm's law. And so, if you remember Ohm's law, which says V equals IR, that's voltage or potential equals the current times the resistance. And so now we know our voltage, we know our resistances, and so we can find the current through this loop. So let's go ahead and plug in the numbers that we know. And I'm going to go ahead and do a little bit of algebraic manipulation and just say I, and I'm going to call this I100 because that's going to be the current through the 100 ohm resistor in our original circuit. It will also coincidentally be the current through the 5 volt source because the 5 volt source and the 100 ohm resistor are in series. So let's go ahead and write the equation down. I100 equals V over R, so V is going to be 5 volts, and R here is actually going to be another equivalent resistance, which is going to be the sum of these 2 resistances. So 100 plus REQ, 100 ohms plus REQ 194 ohms. And if you go ahead and do out that math, then what you will get is 0.017 amps approximately, and we'll go ahead and write that in terms of milliamps, so 17 milliamps. So now we know the current, and we can go ahead and label that on our original circuit. So here we go, we have 17 milliamps here, we have 17 milliamps there. Now we need to determine the current through both of these resistors over here on the right. So we'll go back to our original circuit, and what we can do is we can remember back to Kirchhoff's current law. If we have a node, let's say we form a node right here, any current going into that node has to be balanced by currents going out of that node. So between these two branches, we're going to have 17 milliamps of current. And in fact, what happens when you have a parallel pair of resistors is you form what is called a current divider. And a current divider divides the current amongst those two branches proportionally. And so if we have 17 milliamps coming in, then what we're going to do is have an inverse proportion to the different resistors. So I, 470, that is the current through the 470 ohm resistor, is actually going to equal 17 milliamps, that's the total current coming in, times the opposite resistance, the resistance of the opposite branch, which is going to be 330 ohms, divided by the sum of the two resistors. So 470 ohms plus 330 ohms. And if you do out the math on that, that works out to be approximately 7 milliamps. And so now let's go back once again to Kirchhoff's current law. Now we know that this branch current is 7 milliamps. And so if we have 17 coming in, 7 milliamps going out, what do we have here? Well, simply 17 minus 7. So that gives us 10 milliamps. And let's look at that and see if that makes sense. Well, we have more current going through the least resistant path. And that makes a lot of sense. Electrons like to follow the path of least resistance. So we have more current going through the path of least resistance. So that makes sense. And now that we have all of the currents, let's go back and simply plug in Ohm's law and figure out our other voltages. So we can plug in Ohm's law to figure out the voltage drop across this 100 ohm resistor. And so we have V equals IR again. And so V100, that's the voltage drop across the 100 ohm resistor, is going to equal current 17 milliamps times resistance 100 ohms. And that works out to be 1700 millivolts. We have to carry the milli through. Ohm's law requires that we have things in base units, or if we have any prefixes like milli or kilo, that those get carried on through. So since we have 1700 millivolts, that simply equals 1.7 volts. So we have 1.7 volts dropped across this 100 ohm resistor. Let's go ahead and draw that. We have 1.7 volts. Now let's go back and recall Kirchhoff's voltage law. What Kirchhoff's voltage law tells us is that around any closed loop path, you have no net change in potential. So if we start over here in this corner and we go through this 5 volt supply, we're gaining 5 volts of potential, and over here we're losing 1.7 volts of potential. And then if we come back down through here, we have to balance that out. So simply 5 volts minus 1.7 volts gives us over here a drop of 5 minus 1.7, 3.3 volts. And if we remember back to our properties of parallel resistors, the voltage drop has to be the same if these two resistors are in parallel, because they share 2 points, 2 common nodes. They share this node and that node. The change in potential between the two nodes is the same, and so the voltage here is also 3.3 volts. So we have this shared amongst those two resistors. So now we've determined all of the currents and all of the voltages. We have 17 milliamps coming through this 5 volt source, which gives a gain of 5 volts of potential. We have 17 milliamps going through a 100 ohm resistor, which results in a drop of 1.7 volts. And we have 2 resistors in parallel, both with a drop of 3.3 volts. This 470 ohm resistor with a 7 milliamp current coming through it, and the 330 ohm resistor with a 10 milliamp current coming through it. So that completes our analytical solution. Stay tuned for part 2, where we will build this circuit and we will test it out in the lab and see how close our measured data comes to our analytical data.